So remember that an m-dimensional smooth atlas on a topological space is an open cover of the space together with local charts, i.e. homeomorphisms from that open set into an open set in Rm, having the property that on the overlap where you can compare these two charts, the transition functions going from the one chart to the other are smooth maps. Smooth meaning that all higher partial derivatives exist. So the second derivative, the third derivative, the fourth derivative, and so on. All right. So, and then we said that the purpose of an atlas is that it allows us to say when a function defined on our space is smooth, namely we say that such a function is smooth if relative to all charts, this function expressed in the chart, i.e. you first go back from the chart into the manifold and then you apply the function, so you get, that's this composite map. This composite map here is a smooth map from Rm to R, or at least from an open subset of Rm to R. What does that mean? That just means all of its higher partial derivative exists. And then we said that two smooth atlases on the manifold on the topological space M are equivalent if they agree on which functions are smooth. And then we defined an m-dimensional smooth manifold to be a topological space equipped with an equivalence class of an m-dimensional smooth atlas. Okay. Good. We also talked about smooth maps between manifolds. We said what it means for a smooth map to be a diffeomorphism. That means that the inverse map must exist and must also be smooth. Gave our first example being the two-sphere. We'll come across that again later today. We gave two charts for the two-sphere and we calculated these charts were using stereographic projection, and we calculated the transition functions, and they were, in principle, you're supposed to check that the transition functions were smooth. So, any questions about that? Yeah. Okay, we did an example of a smooth function on S2, just the function which just reads off the z coordinates. And we saw that in the chart, one of the charts, the Northern Hemisphere stereographic projection chart, it sends xy to x squared plus y squared minus 1 over 1 plus x squared plus y squared. So this is a smooth function. So that's why this is a smooth map. Okay, so that was one example of a smooth manifold, but then a whole generalization of this is whenever you can carve out a subspace of R to the m plus 1, but just where a certain function is equal to a constant. So you take some smooth function from R to the m plus 1 to R. For example, the two-sphere, right? The two-sphere is a function from R. The underlying function is a map from R3 to R, which just sends x, y, z to x squared plus y squared plus z squared. And then the inverse image of 1 there would then be the two-sphere, right? So this is just a generalization of that. So now we're talking about a hypersurface living inside Rm. And not any function will do. We need to make sure that the gradient of this function on the hypersurface, remember what the gradient is? It's just the vector formed from the partial derivatives of the function. We need that gradient vector to be non-zero as a vector. So all its components must be, well, none of its, you're not allowed to have that all of its components are zero. So as long as the gradient vector is non-zero at every point on the hypersurface, then it will naturally be a smooth manifold. Okay, so I've drawn a picture of that there. Just stop me at any point here if you just want to ask a question. I'm just doing a quick review. Okay, for example, then, like the torus in R3 would be an example of a hypersurface. Okay, then we spoke about tangent spaces. the tangent space at a point of a smooth manifold is the set of equivalence classes of curves through that point. Two curves are equivalent if in some chart, when you consider the curves in that chart, they have the same tangent vector at that point. In other words, because we know how to calculate the tangent vector of a curve in Rm, we just take the derivative at t equals 0 of this curve in Rm. So if the blue curve in Rm and the red curve in Rm have the same derivative at this point here, then we consider those curves to be equivalent. Okay, so basically just considering the curve up to first order. The set of equivalence classes of curves through this point x, yeah, that's the tangent space at x. And that is a equivalence relation, so we get a set, and it's actually a vector space because you can give a bijection between that set and Rm just by taking, in one of your charts, taking an equivalence class of curves and mapping it to the actual vector in Rm, which is the tangent vector of that curve. That vector that you're getting out is obviously going to depend on the chart that you used. If you use a different chart, you'd get a different vector, but it is at least a bijection. So given a chart, we do at least get such a bijection. And then we can pull over the vector space structure from Rm back onto our tangent space. And that vector space structure, i.e. how to add vectors and how to multiply them by scalars, that will be independent of the chart that you used. Okay. Then we said if you've got a smooth map between manifolds, then you get the derivative at every point, which is going to be a map between the tangent spaces. Sometimes we write it as f lower script star instead of d subscript x of f. So how is it defined? It takes an equivalence class of curves gamma and just maps it to the post composite of f with gamma. So first you do f, then you do, so first you do gamma, then you do f. That will give you a curve in the target space, right? So the picture here is I've got a curve in x, that's gamma, and then I just apply f, that's going to then give me a curve in n. So this equivalence class of curves here, that's what the derivative does to this curve here. And this equivalence class to that equivalence class. Literally just applies f to your curve. So that's a very elegant definition of what the derivative does. And it's very easy to check from that definition, for instance, the chain rule, that the derivative of a composite of smooth maps is the composite of the derivatives. Okay. Okay. Then we did the tangent bundle, which was the idea that to understand that the collection of all the tangent spaces of the manifold, actually it's itself a manifold, but now a 2m dimensional manifold. Right? What is the tangent bundle? It's the collection of all pairs like this, where the first element is just a point in the manifold, and the second element is a point in the tangent space, or a vector in the tangent space at that point. So that's what it is as a set, and then you can put charts on this set, namely a pair x comma v gets mapped to phi of x, so comma the derivative of phi applied to v. So that gives us a chart for the tangent bundle. And I explained what that was, and in that way, the tangent bundle became a manifold in its own rights. Okay, and then the tangent bundle isn't just any old space. It has a natural projection map down to the base manifold, which just sends a pair x comma v to x. Right, so a tangent vector at x can then just get sent to the point x. And a smooth vector field on the manifold is then defined to be a section of this bundle. In other words, a map from the base manifold up to the tangent bundle having the property that it's a section of the projection map. In other words, if you first do X and then you do the projection, that's the same as doing the identity map on M. That's just a fancy way of saying that at each point in M, at each X in M, you're selecting a vector from the tangent space at X. But now having these charts has allowed us to be able to say what it means for X to be smooth. Now we can say it's a smooth map between manifolds. Okay, so a vector field is just a smooth selection of a tangent vector at every point in the manifold. Okay, so some important examples of vectors in tangent spaces and also vector fields is if you do have a chart for the manifold, then you're going to always have these coordinate tangent vectors, which are just obtained by, if you think in terms of curves, say the curves where you just change one of the coordinates and don't vary the others. Okay, and those are actually going to be a basis for the tangent space. So here, for example, is we have change x1, and here's where I change x2. And at each point, I'm going to get these vectors living in the tangent space, and they will be a basis for the tangent space at each point. If you use a different coordinate system, you get a different basis for the tangent space. Okay, so that means that we can express any vector field as a linear combination of these basis vectors at each point. And you can check that for X to be smooth in the sense I described it earlier is exactly the same thing as to say that these components have to be smooth functions. And then we did an example on the two-sphere where you, for example, had the latitude and longitude coordinate basis. And you also had the del X and del Y coordinate basis coming from the XY coordinate system on that particular chart. Because you can just project, you can take a point here and you can just project it to XY coordinates. So you forget about the Z coordinates. And that would then be a chart defined on the northern hemisphere. Computed what the coordinate basis vectors of the theta phi system were relative to the XY system. Okay, and then I wanted to generalize the idea of the tangent bundle to arbitrary vector bundles. So I want to take the idea of the tangent bundle, namely it was a special kind of manifold, namely it came with a map down to the base manifold, having the property that each fiber was a vector space. So it was a bundle of vector spaces. So we can axiomatize that to the concept of a vector bundle over a manifold, basically a smooth bundle of vector spaces. Every point in the manifold, you've got a vector space. And the only condition is that this collection has to be smooth and locally trivial, meaning that around every point you can find an open neighborhood such that the bundle restricted to that open neighborhood is actually just the product bundle. Okay. Just some notation. If I've got a smooth vector bundle over the manifold, then I'm going to write C infinity of M comma E to be the smooth sections of that vector bundle. The slight abuse of notation, because you might think that this means all smooth maps from M into E. I don't quite mean that. I mean smooth maps from M into E such that they are sections. So in other words, do the smooth map and then you do the projections, the identity. But I think it'll be clear in every context what I mean. Okay, and then the last thing we did was this multilinear algebra, and this was maybe the most important thing. And I asked you to go and work through this appendix, because this is the kind of stuff that's not really done in undergraduate linear algebra, but it is really important when you're working with smooth manifolds. So the first thing that you need to know is that for any vector space, you have the dual vector space, which is just linear maps from your vector space into the ground field. And for us right now, our ground field is R, the real numbers. So this is itself, so it's a space of functionals, linear functionals on V. And if V is a finite dimensional vector space, then, and if you've got a basis for V, then you've got the dual basis for the dual vector space. Okay. Also, given any two vector spaces, we can take their tensor product as we defined last time. Okay. Not every vector in the tensor product space is a pure tensor, but every vector is a sum of pure tensors. So for example, this particular vector cannot be written in the form V1 tensor V2. That was an exercise. And if you've got a basis for V and another basis for W, then their tensor products will be a basis of V tensor W, which tells us that the dimension of V tensor W is equal to the product of the dimensions of V with the dimension of W. Whereas if you do, for example, the Cartesian product of V with W, the dimension of V Cartesian product W is equal to the sum of the dimension of V with the dimension of W. Right, so let me just write that down, just to be clear. Right, you can also form a Cartesian product of vector spaces, also known as the direct sum of vector spaces. Right, what is that? How is that defined? The set of pairs, where the first element in the pair is in V, the second element is in W, and addition is done component-wise. And here, a basis will be these guys here. Right? So that means that the dimension is going to be the sum of the dimension of V plus the dimension of W. Yeah. So usually we do this in undergraduate linear algebra, but we don't do this. Yeah. So there we've learned about duals and tensor products. We also got the tensor algebra, which means I can just start with a vector space and then just consider iterated tensor powers of that vector space with itself. And in a silly way, that's an algebra because I can take two vectors and multiply them together by just tensoring them together. And clearly that's going to be an associative operation, so this becomes an algebra. And then there's a certain ideal in that algebra, and I can quotient the tensor algebra by that ideal, and that gives me what's called the exterior algebra. And the exterior algebra itself breaks up into its homogeneous components, and we worked out a basis for the exterior algebra. So if you want to look at the kth exterior algebra, then if you've got a basis for V, then these guys here, these wedges, where you've got to order them so that each successive index is less, or each index is less than its following index. Otherwise, we'll be overcounting. So you get all sorts of really important facts. For example, if you take the dual space of a vector space and tensor it with some other vector space, then that's canonically isomorphic to linear maps from V to W, as long as your vector spaces are finite dimensional. You'll always get a map this way, but it will be surjective when V and W are finite dimensional. Okay, here's another nice exercise, which was that all these things are functorial. So if you've got a map from V to W, then you can, for example, calculate its kth exterior power, which is going to be a map from the kth exterior power of V to the kth exterior power of W, defined like this. I take a wedge, I take of k vectors, so V1 wedge, dot, 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 wedge Vk, and I just send it to A applied to V1, wedge A applied to V2, wedge A applied to Vk. That's how I do it on wedge products, and I extend it to all of the k exterior power of V by linearity. Okay, so then the exercise was to show that we can express this concept of the determinant of a linear map from a vector space to itself, which is something we do in undergraduate maths, in this language of exterior powers. So if your dimension of your vector space is m, then you can take its top exterior power, Why do I say top exterior power? Because if you try to go one higher, this is considered, so if the dimension of V is M, then that implies that, for example, the M plus 1th exterior power for exterior of V is just a zero vector space. Why is that the case? Because if you think what would be a basis for this space, it would be vectors of this form. This vector is going to be the index here, it's going to be less than the index here, and so on. And now I've run out of room. I've got nothing left. So I can't form, so that means there aren't any basis vectors, i.e. it's a zero vector space. Another way of saying it is that a wedge of k vectors is equal to 0 if and only if those vectors are linearly dependent. And in an m plus 1 dimensional, so in the m dimensional vector space, any collection of m plus 1 vectors are linearly dependent. So that means their wedge would be 0. Okay, but so you do have the concept of the top exterior power, and then I can ask and that's going to be a one-dimensional vector space, right? And if I take a basis for V, then this would be a basis for top exterior power, right? It's just a single basis vector. So I can ask what the top exterior power of my linear map does on that basis vector. Here's my formula. And the claim is that when you compute it, well, since I've just got a map from a one-dimensional vector space to itself, any such map would just be a scalar multiple of the identity. And the claim is that the scalar multiple is going to be the determinant of that map. Okay. Maybe let's just go through that little calculation quickly. See that everyone's on board here. So let's E1 up to EM be a basis for V. What I'm trying to do is I'm trying to calculate, okay, and A is a map from B to V. Linear map. Now, how do we define the determinant of A? In undergraduate math. I think you'll agree with me that the first thing is we convert A into a matrix, right? And then because what we do tell the students what to do is how to calculate the determinant of a matrix. And so how do we tell them what the determinant of a matrix is? Well, at least at Stellenbosch, we only really define it for 2x2 matrices, and well, no, we do define it in general, right? It's this it's the sum over all permutations of, let me write it like this. And then you've got the sign in front. Okay. So I want to see that I'm going to recover this from taking the top exterior power of A. So let's see what the top exterior power does. Top exterior power of A, when I apply it to my basis vector, just to be clear, here's my vector space B, and I've got these basis vectors here. Right? This is m-dimensional space. And I've got the top exterior power of V, so A is a map from this guy to itself. Top exterior power of V is just a single basis vector. And I've got the top exterior power of A is a map from that one-dimensional vector space to itself. And I'm calculating what it does to this basis vector. By definition, what does it do? It just applies A to each basis vector in the wedge. Okay. Now, I've got to insert definition of how A acts as a matrix on this basis. So that would be, for example, this here would be the sum. Let's write it as sum over I1. Right. Have I made a mistake so far? Oh. Any comments? And now I've got to then rearrange this. In the end of the day, I'm just going to get out some number times this vector here. That's the only basis vector. See, what's going to go on here is we're going to get a bunch of terms. Let's just carry on. So if I get a sum R1, sum of all possible indices there, and then I've got this going on here. So if you'll allow me to, yeah. Okay. I've got Audrey in the audience with me here. He's frowning at it a bit. What are you frowning about? Let's do it a more simple situation. Let's call our matrix A11, A12, A21, A22. Okay. So then I've got a two-dimensional vector space, and I want to know what AE1 wedge AE2 is going to be. So this is going to be A of E1 is going to be A11 E1 plus A21 E2 wedge A12 E1 plus A22 E2. Right? So then that's going to be, yeah, I get a sum of this form. That's what I'm trying to say here. Okay, but in the sum, you see that sometimes you're going to get terms like E1 wedge E1, right? That's going to go away because the wedge of two vectors with themselves is 0, right? And you also got to take into account that, for example, that this is E1 wedge E2, the minus sign. And in general, if you've got a bunch of vectors that are wedged together and you want to put them into some canonical order, then you're going to pick up a sign which is going to exactly be this permutation here. Okay, so that's how you can see we're going to get exactly this. Right? Because when I rearrange these into the canonical order from 1 up to m, I have to swap them with each other. And every time I swap, I pick up a minus sign. So in the end, I pick up the sign of the permutation. Okay. So this just gives us a basis-free way, at least seemingly basis-free. I mean, in the end, everything ultimately is worked out in the basis, but it just looks like it's basis-free. I mean, it is. It's definitely independent of the basis, but it's when you look at it with the eye, it's more basis-free than our undergraduate definition. Okay, any comments on that? All good. Okay. One last thing, I also I was also asked, I think, by Audrey to give a geometric interpretation of these wedge products. So you want to think, for example, of V wedge W as being the oriented area element spanned by V and W. So the second exterior power or the second wedge power of a vector space, you think of as being the set of oriented area elements in the vector. You see, all that we care about is the area. So for example, this particular oriented element, look, if, for example, if I were to add V wedge W is the same as V wedge W plus some scalar multiple of B. Because what would this be? This would be V wedge W plus T V wedge B, and this is 0, right? So in other words, if I were to take this area element and then add on to W some components in the direction of V, so that would mean I've got this new one here, so I've changed to here, right? So I've added on here a TV component. So that means the new W is this. And so now I'm talking about this area here. This area here is going to be V wedge W plus TV. And you see that the area of the black element is the same as the area of the red element. And that's why we only care about the area. That's the motivation for these rules that we have, that V wedge W is minus W wedge V. So exactly that we can get this equation here. And that means that, for example, that the dual of that space will be the space of area functionals on B. Okay. The second exterior power of V is the area elements. The dual of that space would then be things that assign to an area element a number. So they will be area functionals. Okay, so now that's a review. And Dara's dropped a comment there. Which I can read. And Dara said this thinking in terms of area somehow leads to the area, or the idea of geometric algebra, right? Which is totally true. So there's this concept in physics literature called the geometric algebra, which is a sort of repackaging of the mathematical idea of the Clifford algebra. And yeah, you need an extra ingredient to get to the geometric algebra. So at the moment, when we're doing with wedge products in physics language, they call that the Grassmann algebra. Yeah, so the extra information you need to go to the geometric algebra is also dot products. The dot products and wedge products together form the geometric algebra. That's a more powerful thing than this. Anyhow, so yeah, it's one thing we're going to need in a second, that for any finite dimensional vector space, we have a canonical isomorphism between the kth exterior power of the dual of a vector space and the dual of the kth exterior power of the vector space. Okay, how does that work? If I've got something in here, I want to get something in here. That to get something in here means I have to tell you it's a functional, so I have to tell you what it does when it eats up a wedge of k vectors. And the way I define it is that each of these guys can eat up each of these guys, and I just sum over all possible permutations of the ways that this guy can eat up one of these. Okay. So just to be clear, if your V is two-dimensional, so suppose that E1, E2 is a basis for V, then you've got the dual basis for V star. And E1 wedge E2 would be a basis for the second exterior power V. And I want to calculate what this guy is going to be as an element of the dual of the second wedge of V. I use the definition. How does it eat up two wedges like this? according to the definition, you've got to sum over all possible permutations of how this guy is going to eat up one of these guys. So you could either have this guy eating this one and this one eating that one. That's this term here. Or you could have this guy eating that guy and this guy eating that guy. That's this term here. Now, if we think of what's going on here, this term is 1, this term is 1, whereas this is 0 and this is 0. So what do we conclude? We conclude that under this isomorphism, if you apply it to the wedge of the dual basis vectors, you get exactly the dual basis of the wedge basis. Is that clear? Because it eats up this guy to give you 1. That's what the dual basis, the dual basis of this guy would be the basis such that it eats this guy to give you 1 and anything else gives you 0. So that's what this thing is doing. It's eating this to give you 1. Okay. So once again, just since a wedge of k things represents a k-dimensional oriented area element in the vector space, we should therefore think of something in the kth exterior power of the dual of the vector space as a measuring stick on k-dimensional oriented volume elements in V. And it'll take one of these things and spit out a number. So it's a way to measure areas. There's a difference between an area element and the actual number representing the volume of that area element. The area element itself is a geometric thing. The number that we associate to it would then have to be a function from the set of area elements or volume elements into. Okay. Right. Now we can start differential forms. Okay, so given a smooth manifold M, recall that we've got the tangent bundle of M. So at every point in M, we've got this tangent space, TPM. And a smooth vector field is a section of the tangent bundle. In other words, it's a smooth selection of a vector, xp, in the tangent space at P, for every P. In other words, according to this notation I was speaking about earlier, the collection of smooth vector fields is the smooth sections of the tangent bundle. That's what this notation means. Okay. But now what we've done is we've learned some functorial ways to construct new vector spaces from old. The dual vector space, tensor products, wedge products. So whenever you have some new construction that you can apply to a vector space, that means you could also apply it to a bundle of vector spaces by just applying it to each vector space in the bundle. So that means, for example, we're also going to have, since we have the tangent bundle, we also have the cotangent bundle, whose fiber vector space at a point P is defined to be the dual of the tangent space at that point. Okay, and a smooth one form on the manifold is defined to be a smooth section of the cotangent bundle. So it's a smooth selection of a vector in the dual of the tangent space at every point. More generally, we have the kth exterior power bundle, whose fiber at a point P is the kth exterior power of the tangents of the cotangent space at that point. Cotangent space is just shorthand language for saying for the dual of the vector space. Okay. So any questions here? So a smooth K form on a manifold is a smooth section of the K exterior power bundle. And we write omega superscript K of M for the vector space of smooth K forms on the manifold. In other words, it's the smooth sections of the Kth exterior power of the cotangent bundle. You can see why I needed to talk about vector bundles and stuff so that I could define K-forms. I also need to define joules of vector spaces. I also need to define the exterior powers. Okay, so let's spend quite a lot of time just working through this definition because I think it's valuable. So going to go a little bit slower probably for the rest of the lecture and just work through this, understanding how to actually calculate with these things. Okay, so just revise here. So a K-form consists of a smooth selection of a vector in the kth exterior power of the cotangent space at every point. And it's hence a measuring stick on k-dimensional oriented volume elements in the tangent space, right? Because given one of these guys, it's going to output a number at every point. So in particular, you could integrate it, such a K-form, over a k-dimensional submanifold of M. But we don't need this right now. But that's their first and primary reason for existence, these K-forms, is that they give us things that we can integrate. If you want to integrate over a k-dimensional region, you're going to need to have a K-form, because a K-form is something which at every tangent space eats up a k-dimensional volume element and spits out a number. Okay, so let's just summarize here. What is the space of zero forms according to this definition? Let's work it out here. So the zero forms is going to be the smooth sections of the zeroth exterior power of the cotangent space. Now, what is the zeroth exterior power of a vector space? Right. So I've got a vector space V, and I have to talk about the zeroth exterior power of V. You work through the definitions. Remember, we had the tensor algebra and everything, but at the end of the day, this is just R. Okay. So zero forms is just smooth maps. Smooth maps from M into R. So zero forms is just smooth functions on the manifold. Locally, what does a smooth function look like? If you express relative to a local chart, the function f in the chart, we'll call it f tilde, is going to be a function of the coordinates of that chart. Okay, so what I'm going to go through here is just locally what these geometric objects look like relative to a chart. So a smooth function locally in a chart is just a function of a bunch of coordinates, a many variable function. So just the picture here is I've got a manifold M. Then I've got a smooth function on it. That's F. And I've got a chart locally in the manifold. And then I define F tilde to be this composite here. First you go back and then you come like this. Okay. Zero forms are easy. What about one forms? Well, one forms are sections of the cotangent bundle. What does such a thing look like locally? So for every P in our chart, we have the coordinate tangent vector basis. Right? That we saw that last time, these del x's. So if this is my chart, then I've got these this sort of rectangular grid in Rm, and mapping that backwards via the chart is going to give me a sort of curvy linear grid inside the manifold. And at each point there, I'm going to have a basis for the tangent space. Those are these del x1 up to del xm basis vectors. Fine, so they are a basis for the tangent space. So that means that we have the dual basis for the dual of the tangent space, i.e. the cotangent space. Now, what we were doing earlier was we had a bunch of vectors, E1 up to EM, and then we called the dual vectors E superscript 1 up to E superscript M, right? I'm not using that notation now, and I'll explain that in a second. I'm rather going to call the dual of the coordinate vectors, I'm going to write it as dx1 instead of, I could have written something like this. But anyway, for now, I'm writing it this way, and you'll see why in a second. this is the definition of what these dx's are. They are the dual of the coordinate vector basis. So this guy eats this guy, gets a 1, and when he eats the other guys, gives 0. So that means locally, so they're a basis for the cotangent space at every point. So that means that locally a one form can be written like this, right? It's going to be something times this basis vector plus dot dot plus something times this basis vector, right? So at every point, I've got its components with respect to this basis. I know exactly how this thing operates. It eats up, if you give me a vector, how does this thing eat up that vector? Well, I express that vector as a linear combination of these del xi's, and I know what each of these guys does on those guys. So that'll tell me what this omega does to the vector. Okay, so that's what a one form looks like locally. What about a K form? So a K form is a section of the kth exterior power of the cotangent space. So since this here is a basis for the cotangent space, basis for the kth exterior power of the cotangent space will be given by these wedges here. Wedge, you've got a wedge k of the dx's together. So that means locally a K form inside the chart would look like this. You'd have sum of component functions multiplying these basis vectors. These numbers here are allowed to depend on the point where you're at. So that's what a K form looks like locally. And now it's worth it to go through the example of R3, but I think let's take a 10-minute break and then we'll work through that example. Come back at 3 o'clock. You're welcome to ask me questions in the meantime in the chat. Can I get you something from the Nielsen? Chocolate. Okay. No, no. I'll probably but do I ever, like, can we book the ticket now? Is secured at that level, or should I just preliminary? Most likely, yes. But you were saying something about upgrade, which is some of the international airlines have so normally we have economy and then business and then first class, and but some of these have multiple levels of economy. So, what feature exactly are you interested in? Flexible dates, or I don't remember, but my parents
recently there also, and they said it made a big difference to it was like from basic to like comfort. But I can talk that through. Okay, yeah. 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 The agent will probably know that.
Other than being very sick.
I'm also tired.
Also tired, okay.
And I'm a bit behind on stuff. But, I might have to. I think that form that you want to do.
Yeah.
And I initially said yes there, but my time is looking short, so I have to say.
That's fine. That's not a problem. I actually forgot that you had said yes, so I hadn't had in my mind that you had. Yeah.
I'll definitely still like attend the lectures.
Yeah. Okay. Cool. Okay, so I'm back. I think. Everyone hear me? Okay. So we want to do this example of R3, differential forms on R3. So let's see. The zero form on R3 is just an ordinary function of three variables. A one form is going to be something times dx plus something times dy plus something times dz. And I've just called those somethings alpha x, alpha 1, alpha z. A two form is going to be something times dy wedge dz plus something times dz wedge dx plus something times dx wedge dy. Those are the three basis vectors for the second exterior power of the tangent space of our 3D, right? You know, you can't get a dz wedge dx because, or yeah, it is, but dx wedge dz would be negative of that. Okay, so I've just called them by these labelings here. Okay. In a three form, well, the only basis vector there is dx wedge dy wedge dz. It's a one-dimensional basis vector. The top exterior power of any vector space, now we're in the top exterior power, is always going to be one-dimensional. So I'm going to have some coefficient there which depends on the point. Good. Okay, another thing we need to know is about pulling back of forms. So if you've got a smooth map between manifolds, then you can get the pullback map psi superscript star, which is going to go from k forms on n to k forms on m for every k. So how does it do? How do you pull back forms? So I've got a k form on m, and I'm going to get a k form on n. To get a k form on n, I have to give you something which, when you feed it k wedges, or wedge product of k vectors in a tangent space at n, you must spit out a number. And the number that I'm going to spit out is defined as follows. I take the push forward of those vectors along the derivative of psi, and then I apply omega to that wedge product there. So in terms of the pictures, I need something which is going to eat up a wedge of vectors in M and spit out a number. The way I'm going to do that is each of these vectors, I'm going to push them forward to a vector in N using the derivative of psi, and then I wedge those vectors together, and that gives me something in the kth exterior power of the tangent space in N, and then I let omega, because remember omega was a k form on n, omega was living here, so it can eat up these guys and spit out a number. Okay. So pullback of k forms ultimately defined in terms of push forward of tangent vectors. Okay, so importantly now there's the concept of the exterior derivative. So there's a linear map from zero forms to one forms defined as follows. Remember, zero form is just a smooth function. So it's called D. So I take a smooth function, and I'm going to get a one form on the manifold called df. To say that I have a one form means that at every point P, I have a linear function on the tangent space at P. So I have to tell you what it does to a vector in the tangent space. And what it does, and I should actually make this a definition, is that it takes the derivative of my function in the direction of V. In other words, you take a curve in the equivalence class of B, and you differentiate the function along the curve at t equals 0. And we call this df the differential of f. Okay, so just as a picture, I've got a manifold M here. I've got a smooth function on it. And I'm going to get it, the differential of that smooth function is then going to be a 1 form. That means that at every point P, it's going to be a function from the tangent space at P into R, a linear function. How is it defined? Well, you give me a vector in the tangent space. I remember that such a vector is an equivalence class of curves. And what it does is it differentiates the function along that curve at t equals 0. Okay. Then, of course, you have to check that this is well defined. In other words, it doesn't depend on the equivalence class of the curve that I'm using. Okay. So locally, if you've got coordinates in a chart for M, then you can write my function f as f tilde of those coordinates. And then the differential of f expands in terms of this coordinate basis for the dual of the tangent space as just partial derivative of f tilde with respect to x1 times dx1 plus dot 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 plus the partial derivative of f tilde with respect to xm times dxm. So you may have seen us writing down such constructions in calculus before, but we never really understood what these things were. And now we have concrete interpretations for what these things are. This is no longer an infinitesimal, as perhaps people in the 16th century would have thought of it. It is a linear function on the tangent space. Just a fancy repackaging of the word infinitesimal, but at least now we've expunged the idea of an infinitesimal from our language. Okay. Any questions here? So for example, every coordinate inside a chart is itself a smooth function, right? So if I've got a chart on the manifold, then I could take one of those coordinates, xi, and that would be a function on that chart, a smooth function. And what would be the differential of that function? Well, if we calculate it, we find that the derivative of that function, defined as I've just said in the previous slide, is actually what we were calling dxi before. Before, what we wrote down as dxi, remember, we defined those dxi's to be the dual of the coordinate basis for the tangent space. And now I've got a different notion of what dxi means. It's now defined as the derivative or the differential of the coordinate function. The claim is that these two things are compatible, that the derivative of the coordinate function is actually the dual basis vector, the coordinate basis for the tangent space. So let's do that as a little calculation. So to prove that, to say that something is the dual basis vector, I need to calculate it on the basis vectors and check that I get delta Rj. So let's do that. So I now use the definition of what the differential of a function is. I have to differentiate the coordinate function along the path where we only change xj. And you'll agree with me, that means I'm going to get out delta Rj. Yeah. So that's why I said earlier that I was going to write them like this. Now you see why I wrote it like this, because the dual basis vector is just the differentials of the coordinate functions. The dual basis vectors of the coordinate tangent vectors are the differentials of the coordinate functions. Okay, another thing. So far I've defined the linear map, D, the differential of a smooth function, to take a function and spit out a one form. Not every one form in here is of that form. Sometimes it is, but it depends on the topology of M. But there is some extra property satisfied by this map. It's not just any old linear map from functions to forms. It satisfies the Leibniz rule. In this stage, that means that if I take the product of two functions, what's the differential? Well, you'll find that it's f times the differential of g plus g times the differential of f. And why is that the case? Whenever I have to check whether two forms are the same, it suffices to check it in any local patch, because if it's true on any arbitrary patch, then it's true everywhere. So I can check it locally on a patch. What's nice about checking it on a coordinate patch is then I can expand. Well, I know exactly how to take the differential of a function because I can use this calculation here. Differential of a function on a coordinate patch is just the sum of the partial derivatives of the function in the different directions times the d of those directions. So I do that now to f times g, so equal to this. And then I can use the ordinary product rule from ordinary calculus. And that is separating the sum, writing it like this. And that's then by definition this. So in other words, this is nothing other than just the ordinary product rule, repackaged. Okay, moreover, if I've got a smooth map from manifold M to manifold N, then this pullback operation, which I defined just now, is compatible with the differential operation. Namely, if you pull back the one form df, or let's say it like this, if I start with a function, I calculate its differential to get me a one form, and then I pull that back to get a one form on M, that's the same thing as starting with a function on N, pulling it back to get a function on M, and then taking the differential of that function on M. The only thing you might object to is you might say, what does this thing here mean? All what I mean by that is I just mean f after psi. That's what I mean there. Right? Because f is a function from n into r. So f after psi is going to be a function from m into r. Okay, so let's write this. Let's check this. So the left-hand side applied to a tangent vector v is by definition df on the push forward of v, right? And one thing you can check is that what is that? What is that? That's actually the derivative of f applied to the push forward of v. Okay. So just to be clear here, here's our picture. I've got my manifold M, my manifold N. I've got a smooth map from M to N. I've got a smooth function defined on N. Then I've got a point P in M and its corresponding point psi P in N. That means I've got a map at the level of the tangent spaces from tangent space at P to M to the tangent space at psi of P to N. And what I'm doing is I'm starting with a vector V in the tangent space to M, and I'm wanting to prove this identity. And the way I'm doing it is I'm calculating this guy here, and I'm saying that when you calculate the derivative of a function or the differential of a function, you apply it to a vector, it's the same thing as calculating the push forward of that vector using the derivative of the map. So let's just be clear what that means. So here's my manifold M. Here's my function f. Now I'm at a point P, and I've got the tangent space. So here is what I call f star is going to be a map from the tangent space of M at P to the tangent space at F of P of R. Everyone agree? And now remember that this canonically identifies with R because the tangent spaces of Euclidean spaces canonically identify with the underlying Euclidean space. So in the end, the push forward of F is just a map from the tangent space to R. And one exercise that I should write down is this fact here. That if you calculate the differential of F defined in the way I defined it earlier, remember, I defined the differential of F by, in this formula here, by differentiating along the curve representing the vector. The claim is that, according to that definition, if I calculate the differential of F applied to a vector V, that's the same thing as just calculating the push forward of F applied to V, once I make this identification here. Okay. So that's a really handy fact because it allows us then to then say that this is equal to this. Okay, so I went from this line to this line. So that's what the left-hand side is. What is the right-hand side? So the right-hand side is this by definition, which by definition of what the pullback of F is, it's just this. And now we use this exercise again to say that the differential of a function is just the push forward of that function applied to the vector. And now I use the chain rule for push forwards. F composed with psi pushed forward is the same as first you push forward along psi and then you push forward along F. Derivative of a composite is the composite of the derivatives. So that's how I get that this is equal to that. Okay, any questions? So you can see that differential geometry is just a language. So where are we? We've introduced this concept of the differential of a function, which is a map from zero forms, i.e. smooth functions, to one forms. And we have checked that it satisfies the Leibniz rule. Okay, fine. Now we can extend this map to a map from K forms to K plus one forms. So not just from zero forms to one forms, but from K forms to K plus one forms. And at this more general context, we call it the exterior derivative. So how does it work? Well, each K form is locally a sum of forms that look like this, right? So inside a coordinate chart, these guys are going to be a basis, and then I'm going to have component functions multiplying those basis vectors. Any K form locally looks like this. So I need to tell you how to apply D to a thing like this, and then I can extend it out by linearity. So the way that I do it is I define D of such a thing to be the following. I sum over the derivatives of this component function with respect to the various directions, and then I add a little dxj. So whatever direction I'm differentiating f with respect to, I add a dx in that direction, and then I wedge with whatever remained. So you can see I've got k plus 1 wedges here. Sorry, I don't know why I said im here. It should have been k. So now I've got k plus 1 vectors being wedged together. So that's the definition. And I extend that definition to all of the K forms by linearity. Okay, so of course the most important thing that I have to do here is I have to check that this is actually well defined, that it didn't depend on the coordinate charts I used. Okay, so I've done something slightly evil here, which is that I've used a local neighborhood, or I've used a coordinate system in order to give a definition of what d omega is. And what I'm saying is that actually it's a harmless thing because the answer won't depend on the coordinate system. If I had a different coordinate system, then I'd have, if I had y's, then I'd have to write each of these dx's in terms of the dy's. When you do that, you'll pick up a certain matrix, determinant of a certain matrix, and similarly that would then cancel with the change of variables formula for these partial derivatives. So that's the idea. But you have to check that. Okay, so that's the definition of how to take the exterior derivative of a k form to produce a k plus 1 form. And here's the key point about this construction is that if you do it twice, then it's 0. In other words, if you start with a k form and you apply d to get a k plus 1 form, and you apply d again to get a k plus 2 form, then the result will be 0. Why is this the case? So I'm going to, as long as I check it on forms of this form, then it will be true for all forms. So I apply d to that. So that would be d omega. Second derivative, now I apply d to this k plus 1 form. So now I've got to differentiate this component function with respect to all possible k directions. Well, yeah, with respect to the I directions, yeah. So I've got to differentiate this thing with respect to xi and then multiply by dxi. I've got sum over I. And so the point is that this thing here, this partial derivative, is symmetric in I and j because partial derivative, the second partial derivative of f with respect to xj first and then xi, as I've written it there, is the same as the second partial derivative. We differentiate first with respect to xi and then with respect to xj. What theorem is that, by the way? Can anyone tell me? Audrey is ill. I'm making him more ill. In a sense, I would call that the fundamental theorem of multivariable calculus. Fundamental theorem of multivariable calculus. I think the person, Clorose theorem. Thanks, Dario. I only know this from Stewart's calculus textbook, right? Clorose theorem. But somehow we don't know Cloro very much, right? I remember James Stewart's textbook said that he was a 21-year-old engineer or something and discovered this, but it's like such an important theorem, and I think he deserves to be better known. I'd like to know more about him. But definitely that's the fundamental theorem of multivariable calculus. So that means that this second derivative is going to be 0 because I could then go ahead and group the sum over all I and j into a sum where I equals j. In that case, I'm going to have a dxi wedge dxi, and that would be 0. And then the sum, and then the terms where I is not equal to j, for which there's going to be two contributions: one where I is less than j, and one where I is greater than j. Where I is greater than j, I could just swap their order so that I can write it like this, and then I'd pick up a minus sign, so I'd get this in front, and this term is 0 by Cloro's theorem. Yeah. So the fact that d squared equals 0 is just follows directly from Cloro's theorem. In fact, it's equivalent to Cloro's theorem. So if let's go ahead for R3. Remember, this is what our 0 forms, 1 forms, 2 forms, and 3 forms look like. So let's calculate what D does to these guys. Let's do a little calculation here. So let's see. Let's do it slowly. So on a 0 form, what will happen? I take a 0 form of function, and then I get df. That's just going to be partial derivative of f with respect to x times dx, partial derivative of f with respect to y times dy, plus the partial derivative of f with respect to z times dz. Fine. What happens when I go from one forms to two forms? Well, I take this beta here, and I've got to differentiate it now, but got to calculate its exterior derivative. So I've got this guy here. Oh, sorry. Thanks. So I'll do them one at a time. Let's start with this one here. So I've got to differentiate in the various directions. So I've got to differentiate this guy with respect to x times, and then I've got to put a dx in front. So let's just do that slowly. So it's differentiate this thing with respect to x, and then I put a dx in front. Plus, differentiate him with respect to y, and I put a dy in front. Plus, differentiate him with respect to z, and I put a dz in front. Then I've got to do the same now for this guy here. So differentiate this guy with respect to x. So then I have a dx in front. And then differentiate him with respect to y and put a dy in front. And then differentiate him with respect to z, put a dz in front. And finally, for this guy here, okay. Well, let's just see what's going on here. So we see this term here is 0, right? Similarly, this term here is 0. So in the end, for the next part, I'm going to get okay. So let's add a page here. So I'm going to get out something times dx wedge dy plus something times dz wedge dx. That's just the way I'm grouping them. Plus something times dy wedge dz. What is the thing that's multiplying dx wedge dy? It's going to be this guy here is going to appear with a minus sign, and this guy here is going to appear with a plus sign. So I get dou alpha y, dou x minus dou alpha x by dou y. And for the next guy, I'm going to get dou alpha x by dou z minus dou alpha z by dou x. And here, I'm going to get alpha z by dou y minus dou alpha y by dou z. Okay. So that's how to calculate the exterior derivative of a one form to get a two form. And let's do the last one. But how do I take the exterior derivative of a two form to get a three form? Okay, here's my two form here. Okay, so I've got to apply this formula step by step to each of these three terms. To each term, I sum over the derivatives in the various directions. Each time I differentiate this with respect to a direction, I put a d of that direction in front, wedging these guys. So for example, I've got to do the derivative of this with respect to x times dx, wedging this, plus the derivative of this with respect to y times dy wedging this. But if dy wedges this, then I'm going to get a dy wedge of dy, which is going to be 0. So that's not going to get any contribution. So you'll agree with me that at the end of the day, I'm going to get 3 contributions. From this term here, I'm going to get a single contribution, which is going to be this. From this term here, only contribution is when I'm differentiating this with respect to y, because then I'm going to get a dy, wedge dz, wedge dx. Right? So then I'm going to get this thing here. And I can then rearrange this by letting this x hop over the z. That's going to dz. It's going to give me a -1. And then hopping it again is going to give me another -1. So that'll give me a +1. So that's why I wrote it in this order. So that when I put them back in the proper order, I get a +1. And yeah, let's I can see I've written these badly. Yeah, I should have said this should have been an x here, right? I should have said x there. And then I've got this for the last term. Okay. Any questions about that? Does everyone agree with what I've done? So the question is, of course, where have we seen such expressions before in multivariable calculus? So I'm talking about something like this. Where have you seen such a thing before? You see, what I'm saying to you is that on R3, we can identify the 0 forms on M. Well, that's just the smooth functions on M, as we know. Okay. Then we've got the 1 forms. That's the same. Let's have a look. What does a 1 form look like? A 1 form looks like this. So it's got 3 component functions. What is something that has 3 component functions? Another thing that has 3 component functions that we deal with in multivariable calculus would be a vector field. Agreed? So I can think of a 1 form on R3. Let me write R3 here, just to be clear. This won't be the case in general, but on R3 we can say that a 1 form is in correspondence with a vector field. Right? I can just take those coordinates here and make a vector field. I'll call it alpha, which consists as a vector, it's alpha x, alpha y, and alpha z. See? And similarly, a 2 form also looks like a vector field. I can make a vector field beta, which just consists of beta x, beta y, and beta z. And a 3 form just looks like a function, because this guy is just an ordinary function. So what am I saying? I'm saying that 1 forms on M identify with vector fields on R3. 2 forms on M also identify with vector fields on R3. And 3 forms on M or on R3 identify with just smooth functions on R3 again. And moreover, the derivative map from 0 forms to 1 forms, let's go see what it does. Here's what it does. If I reinterpret this guy as a vector field, then what am I getting out? I'm getting out, if I think of this as a vector field, then this would be the vector field that looks like this, right? Del f by del x. Agreed? What is that called? Gradients. Also written like this. Or let's write it like this. Okay? So this operation is actually just taking the gradients. From 1 forms to 2 forms, what's going on? Well, at the end of the day, here's my 2 form. If I interpret this as a vector field, this will be the first component of the vector field, this will be the second component, and this will be the third component. Where have we seen such vector fields before? Also known as the? Almost. curl of the vector field, right? So this map here is the curl. From one forms to two forms is calculating the curl. And then from two forms to three forms, what's going on here? Here's what D of a two form is. It's going to be this three form here. So the thing in front is a function, right? Where have we seen such a function before? So I took as input a vector field, and I outputted a function, the divergence. So incredibly, with just a single formula for D, which was this formula here, incredibly, that single formula has led to three separate things that we know and love as operations in multivariable calculus. Interpreted as going from zero forms to one forms, it's the gradient. Going from one form to two forms, it's the curl, and going from two forms to three forms, it's the divergence. And also, the single theorem that we proved, that d squared equals 0, which was this sort of three-line proof, now will hold for any d. So in particular, it says that this composite here is 0. So that tells us something that we already know, that the curl of the gradient is 0. Over here, it tells us the divergence of the curl of a vector field, 0. Vector field. Okay, so very cool. You can see why, if you love multivariable calculus, you'll love differential forms. Okay. Take a little sip here. Let's just do a little calculation here, just that we know how to calculate with differential forms. So for example, suppose I consider the function on S2, which just takes a point and just spits out the x coordinate of that point. So I just want to understand what dx will look like in the different coordinate system. So we know that x can be written in terms of the theta phi coordinate system as well. So let me just say it like this. So in the xy coordinate system, so I do have an xy coordinate system, right? So I just use x and y. So that would be valid on this sort of eastern hemisphere of the two sphere, right? We are just associate to a point in the eastern hemisphere, it's xy point. I can't go into the western hemisphere as well, else I'll be having 2 points that have the same xy coordinate. But it is a coordinate chart on this eastern hemisphere. And on that eastern hemisphere, dx, so I've still got this function, and I can calculate its differential. It's obviously going to be 1 times dx plus 0 times dy. But what I'd like to do is express that in terms of the d thetas and the d phis. So dx is the same as partial derivative of x with respect to theta times d theta plus the partial derivative of x with respect to phi times d phi. And here's a formula for x in terms of theta and phi. So if I calculate those derivatives, you see that dx is given by this expression. This is just a little calculation to make sure we know how to compute with differential forms. Good. Let's start complex manifolds. Okay, in the last 10 minutes. So I'm going to take my definition of a smooth manifold, and I'm going to now adjust it to talk about complex manifolds. So remember, what's the definition of a smooth manifold? We first of all started with the concept of a smooth atlas on a topological space. So now I'm going to change this to let's call it a holomorphic atlas. Again, it's going to be an open cover together with these homeomorphisms. Right. And now instead of Rm, I'm going to have Cm. Okay. And then, so here I don't have Rm, I've got Cm. And what I want now is that on the intersection of these charts, the resulting map from Cm to Cm is no longer smooth, but is holomorphic. What does that mean? So as a map between open subsets of Cm, and what does it mean to be holomorphic? So there's a slight subtlety here. I could demand that all higher partial derivatives exist and are holomorphic themselves. That's maybe what I'll write down. But as you know from complex analysis, it's actually sufficient just to know that any holomorphic function implies that all its holomorphic derivatives exist. So I just need to know that this function is holomorphic. Okay. Anyway, it's fine. So that's the definition of a holomorphic atlas on the space. And again, what does the atlas do? An atlas on a topological space allows us to say when a function is, so let's say a holomorphic atlas on a space, allows us to say when a function is holomorphic. Namely, we demand that for all charts, such a map in the chart is a holomorphic map from an open subset of Cm to C. Okay. Everybody following me? Two holomorphic atlases are called equivalents if they agree on which functions are holomorphic. And an m-dimensional complex manifold is a topological space M equipped with an equivalence class of an m-dimensional holomorphic atlas. So that means that locally the space looks like Cm, not Rm. Of course, if you are a complex manifold, and in particular you will also be a real manifold, but then you'll be a real manifold of dimension 2m. Okay. So that's the definition of a complex manifold. Any questions about that? So what about maps between complex manifolds? So a map between complex manifolds is holomorphic. Not just a map to R, but a map from M to N if locally you get a holomorphic map from Cm to Cn. What does that mean? That just means you've got a bunch of components, and each of those components must be a holomorphic function, a holomorphic many variable function. What is a holomorphic many variable function, you might ask? So something like this. What does it mean to say that such a thing is holomorphic? It just means that when I fix any one of the variables, if I fix m minus one of the variables, and I let the mth one be my independent variable, then that must be a holomorphic map from C to C. Okay. So a holomorphic map between complex manifolds is called a holomorphic diffeomorphism. if the inverse exists and is holomorphic. Okay. So just to give a nice example, the example that I want you to always keep in mind about our favorite smooth manifold is the two-sphere, and it's our favorite complex manifold as well. It has complex dimension 1 as a complex manifold. Of course, locally, I'm going to show that we're going to see that the two-sphere is locally holomorphically diffeomorphic with complex plane, right? So instead of going to R2, I'm going to call it the complex plane now. And I'm going to take the same formula and just rewrite it now like this. So I want to write this. This is now an element of R2, and I'd rather write it as an element of the complex numbers. So that's easy enough to do. I can just say it's this. Pretty happy? The inverse map would then do this. There's the complex plane here. Fine. This is going to be a holomorphic atlas. So that's what it does on the northern, the northern hemisphere. I can't be projecting from the North Pole. I've got to be projecting from the, something's gone wrong here. So this is, I'm supposed to remove 0, 0, 1 here, and here I should be removing 0, 0, minus 1. Okay. So there is a subtlety here, which I want to point out, which is that if I use the same charts as I used before, then you'll find that when you compute the coordinate change maps, right, let's just be clear. I've got a map into C here and a map into C here from the northern hemisphere at the top and the southern hemisphere at the bottom. And I'm going to get a resultant map from C minus the origin to C minus the origin here. And if you compute that map, it's actually going to send Z to 1 over Z bar. And that's a problem because that's not a holomorphic map. If I've got a holomorphic map, the easiest way to check that it's holomorphic is that it should just be able to write it as a function of Z out using Z bars. If you need to use Z bars to write down your formula, then it's a sign that your function is not holomorphic. So I have to adjust these charts. The conclusion is that stereographic projection from the North Pole and stereographic projection from the South Pole don't give me a holomorphic atlas for the two-sphere. Where I would have to adjust it is I have to make one of them a bar. So instead of doing stereographic projection from the North Pole, I'm going to take that and then I'm going to do a complex conjugate on that. That's going to fix my problem. So here I would then put a minus sign there. And now this map would go send 1 to 1 over Z. You should all check this in the exercises, right? Okay. So that's our first example of a complex manifold. And if you understand S2, then you'll understand everything. I think we should stop here. I will upload the notes and I will just send you you can just, I won't send you another email. You just look, it'll be up